AI boom is absolutely everywhere, right? It promises to change, well, everything. But behind all the incredible algorithms and these mind-bending language models, there's a huge problem brewing. And it has nothing to do with code. It has everything to do with raw physical power.
You could argue that the single biggest thing holding back the AI revolution isn't better software. It's the power plug. It all comes down to whether our physical, electrical infrastructure can actually keep up with AI's incredible and incredibly volatile thirst for energy.
So let's get into it. See, the problem isn't just that AI uses a ton of electricity. We kind of knew that. The real issue, the thing that's causing all the headaches, is the way it uses that power. It's not a steady, predictable hum. It's chaotic, it's unpredictable, and our grid just wasn't built for it.
And just to give you an idea of the scale we're talking about, a single server rack, just one, can pull over 100 kilowatts. That is an absolutely immense amount of power packed into a tiny space. And that's not the exception anymore. That's becoming the new normal for any serious AI data center.
Think about it like this. Old school data centers were predictable. They drew power at a nice, steady rate, easy to manage. But AI, it's the complete opposite. Its power needs can literally double or get cut in half in the blink of an eye. And those sudden surges are what can wreak havoc on the grid. Okay, so to really get why this is such a big deal, we need to look at the two main jobs an AI is doing, because each one has its own very unique and very challenging power signature. On one side, you've got model training. This is the marathon. It's a long, brutal grind that sucks down huge amounts of power consistently for days, sometimes even weeks. Then, on the other side, you have inference. This is the all-out sprint. It's when the AI answers your question or generates an image. It's a short, massive, and totally unpredictable burst of power. So you put that marathon and that sprint together, and what do you get? You get this wild, spiky, and completely unstable load profile. You've got these super fast ramp-ups, sudden drop-offs, and these crazy overload bursts. This is the chaos that our electrical grid is now facing. And frankly, it's not ready.
So what happens when you try to force this chaotic, spiky power demand through an electrical system that was built for calm and stability? Well, you guessed it. Things start to break. And it's a cascading failure, from the huge public grid all the way down to the tiny components inside the data center.
See, this is how we used to build things. In this traditional setup, the backup power system, the UPS, it only protected the servers. That made sense back then, because the cooling systems used a nice, steady amount of power. But with AI, the cooling has to ramp up and down just as wildly as the processors, and in this old design, it's left completely unprotected. So the first thing to feel the pain? The entire public grid. When a massive AI data center suddenly gulps down a city's worth of power, it can cause voltage to drop and the grid's frequency to wobble. Worst case, the utility company has to start cutting power to prevent a total collapse. We're talking widespread outages. And the backup generators? They're not happy either. These things are built to run at a steady pace. This constant, violent change in demand, it's like taking your car and just flooring the gas pedal, then slamming on the brakes, over and over and over. It causes incredible stress, burns more fuel, and just wears them out way too fast. And even the last line of defense, that smaller UPS, gets pushed way past its limits. It starts to overheat, its parts wear out faster, and this is the crucial part. It doesn't do anything to protect those all-important cooling systems that keep the AI chips from literally melting. Basically, the old approach is failing at every single point in the chain. Okay, so that sounds pretty bad, right? But here's the good news. This problem is not unsolvable. And the solution, funnily enough, comes from heavy industry. Places that have been dealing with massive, fluctuating power loads for a long, long time. It's all about building for resilience. The change in design is actually pretty simple, but it is a total game changer. Instead of that little UPS just protecting the servers, you put a big, beefy, static, medium voltage UPS way earlier in the chain. And what does it do? It protects everything, both the AI servers and their critical cooling systems, the whole shebang. So what is this thing exactly? Well, a static MV UPS is basically an industrial-strength power conditioner. But its most important job here is to act like a giant shock absorber. It sits right between that chaotic AI workload and the sensitive grid, and it just soaks up all the volatility. and you can literally see the difference it makes. It's incredible. The UPS takes in that crazy, spiky, unpredictable load from the AI servers, and on the other side, what it shows to the grid and the generators is this smooth, gentle, controlled ramp-up of power. It turns all that noise into a clean signal. So, just by rethinking the architecture, by putting that shock absorber in the right place, this new approach just systematically knocks down every single one of the problems we just talked about. It creates a stable, resilient environment where AI can do its thing without threatening to take down the whole power grid.
So, let's just recap. First, it protects the grid by absorbing all those sudden power spikes. Second, it protects the backup generators by giving them that nice, smooth load they were designed for. And third, its tough-as-nails industrial design is more than capable of handling the crazy demands of both the AI servers and their cooling systems combined.
The bottom line is, this isn't just some patch or a quick fix. It's a fundamental upgrade to how we think about the power chain. It's about building in resilience from the ground up. Because in these modern data centers, managing the power is now every bit as critical as processing the data itself. Now, this is a fantastic solution for the challenges we're facing today. But as AI models get exponentially more powerful, we know their appetite for energy is only going to grow. And that leaves us with a really big question. As we build this incredible future of intelligence, are we also building an electrical foundation that's strong enough to actually support it?